we are discussing this very nice blog by Christopher Olah. And it is about networks, neural networks, manifolds, and topology. Sort of shows the link between these three things. Now, neural network is something we have been introduced to in the first 2 weeks. You probably don't know what a manifold is and what topology is. Anybody here with a background in manifolds and topology? So I'll just give you a very simple.
So Asif, I think it is the study of the shapes, right? And how like it deforms, and if it like even if it changes the shape, if it does not, geometry does not get deformed, like you have to poke hole to actually understand the behavior.
Yes, that is a pretty good understanding of it, close to it. Huh? What you're saying is the homeomorphisms, and that is one of the, or diffeomorphisms more like it. Those are the things that we will talk about today. Right? Okay. You will see me introduce a few words that are at the heart of machine learning. See, in machine learning, and this paper sort of alludes to it, but doesn't get too much into it, there is a fundamental hypothesis. All of machine learning is predicated on a hypothesis. It is called the manifold hypothesis. If this hypothesis is not true, machine learning would essentially not be possible. Right? So what is this hypothesis? We are going to understand it in a little bit. But before we do that, let's try to understand a few things. What is a manifold? B, what is a topology? What is the topology of it? Topology of it. When we say topology of a manifold, what do we mean? Manifold. And then C, we'll talk about things like homeomorphism, and diffeomorphism. Diffeomorphism is something this blog did not mention. Diffeomorphism. This is actually more relevant to neural networks, actually. They're not just homeomorphisms, they're like diffeomorphisms. So what are these things? We will understand that. And what is the relationship, I suppose, machine learning to manifolds and topology? So imagine that you have an elastic sheet. I'll just take a square sheet, but it can be any shape, right? And in that sheet, you have, let's say, a shape, round shape. Right? This is, let's say, a shaded red, and this is white. Suppose I say it is stretchable sheet, rubber sheet, or elastic sheet, somehow. Think of it like this. If I ask you, can you make this look like this circle to become an ellipse? So how would you do that?
You can stretch it.
Yeah, you can sort of stretch it, and you can say, there we go. It has become this. Are we together? Right? So now it has become an ellipse. What you have just done is a transformation. You would call it both a homeomorphism and a diffeomorphism. Diffeomorphism is a smooth transition. So let me just call it a diffeomorphism into this particular shape. Because you can think of, in some sense, that this state represents a state in which the ellipse, so let me parameterize it with a time that goes from 0 to 1. At 0, it is this red circle, circle. At 1, it is the ellipse. Right? So this is t is equal to 0 state, t is equal to 1 state. So you can say that in some sense, you could say that equation of this is 1 minus t, the circle, if we say that the circle manifold, the initial manifold, plus t times the ellipse manifold. Right? Let's see if this equation makes sense. This is a mapping from 0 cross 1 times, this is what, a 2D space, going to a two-dimensional space. Well, I wrote some fancy mathematics here, but what I'm seeing is very simple. This R square is the sheet, this rubber sheet. And this R square is, of course, the target stretched out rubber sheet, isn't it? And now we are saying that actually this is a mapping in which you have a continuous deformation of this into this, parametrized by a factor t. So now in this equation, try putting t is equal to 0. What do you get at t is equal to 0? You will get the circle. At t is equal to 1, when you put t is equal to 1, it will become the ellipse. Does this make sense, guys? Think of this equation, and it's a very simple equation. I'm saying that as you increase t from 0 to 1, initially it will look like a circle, and gradually it will start looking like an ellipse. Does that make sense, guys?
Yes.
It does make sense, right? So this is a classic example of saying that we have performed a homeomorphism. And usually when it is done in a very smooth way, it is not just a homeomorphism, it is a diffeomorphism, right? So we can be a little bit more exact about it. Now, generally, smooth transitions are preferable. If we can get away with smooth transition, it is really very good. Now, if you understand this much, then let us add some wordings to it. This is, I did it as a 2D surface, but suppose it was curved. This is in a higher dimensional space. Right? This was just the plane here. So here was your circle. I'm just doing the same thing. Gradually, I'm taking you there. So this is your red. It's the same thing, but now there is a third axis. This is x2, x3. Right? Now, suppose I say that you can deform it into, like, take this and make this circle sort of bulge out. Can you do that? Can you just sort of start pulling here, pull up, and create this red bulge here, right? A red bulge. Can we do that?
Yes.
We can do that, right? All you have to do is take this and just put something underneath it and gradually start pushing it up. And now you have ended up with a surface that has gone from this to a much higher dimensional space. It's the surface is occupying a three-dimensional space now, this manifold. Right? And yet, even though it's occupying a three-dimensional space, you would say that it is still, in itself, it is two-dimensional. The property of that rubber sheet has not changed. It is just occupying a higher ambient space. So the ambient space, the outer space is, ambient space was a three-dimensional. But in the beginning, it wasn't occupying, or it had no presence in the third dimension. But by making a little bit of a push here or bulge here onto the red part, now you have occupied all the whole ambient dimension. All three things are there. But you would still say that the same essential quality of this elastic sheet has not changed. So when you say that the essential quality has not changed, you would say that the topology has not changed. Topology is the overall quality that remains invariant to stretching and bending and all of that. Are we together? So you can smoothly stretch and bend and do whatever, like for example, we bent it up, do whatever you want, but it remains what it is. Just don't tear it. You can't bring a knife to it. Are we together? So long as you don't bring a knife to this sheet, everything that you do preserves the essential quality of the sheet, because it's a reversible change. You can go, if you can go from here, you can go back also. Would you agree? Right? So this can go here, but it can also go back. So these are reversible changes.
Right
So
question.
Asif, yeah, so is it like a way of, like, can we say that, is it like a 2D manifold embedded in a 3D space?
This rubber sheet is a 2D manifold that was initially embedded in a 3D space, and this is now occupying all 3D space. A significant part of all the, it's gone on and occupied the third axis also.
Okay.
But it is still embedded in 3D space. It is a 2D manifold embedded in 3D space. So
Okay.
somebody else asked a question.
Yes, I wanted to ask someone. So how is topology related to geometry?
I will come to that.
Okay.
See, these fields, I am giving you a geometric way of looking at topology. Actually, let me answer that. When you look at topology, the initial version or the way it is taught, it starts with something called point set topology. So people start very abstractly with algebra, right? And then they develop it from there. Whereas what I'm doing is I'm giving you a geometric interpretation of topology. In a very geometric way, I'm showing you what topology means. Really?
Correct, sir.
So I'm not saying let this be a set of points and blah, 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 and then it is, these properties hold true and so forth.
No, so my question is like, even though, I mean, the geometry won't change of the object, even though we can bend and do all sort of things with an object, right?
Yes. The geometry, not the geometry, the essence, the geometry is changing. No? You look at the shape has changed. But you see that
Shape
the
is changing.
topological property hasn't changed. Topologically,
Mm-hmm.
it's still the same rubber sheet. It has just been stretched. You have introduced a bulge with your hand.
So what is topological property, sir? Like when we say that, what is the property?
So let us take an example of a topological property, right? See, suppose I take a rubber sheet which is solid like this, right? So let me take this example. Consider A, this is a solid rubber sheet. And now think of another rubber sheet which has a hole in it. Now, is there any way that you could deform one into the other? Any kind of stretching that would cause this to happen?
No.
It can't. I mean, the only way you can do it is you can stretch it to the limit so that it perforates in the center.
Correct.
That's a catastrophic event. It's not a continuous deformation. There is no way you can deform this into this. So you say that this is the topology of this A is inherently different from topology of B. Right? People use some fancy language, homotopy and so on and so forth. Let's not go into that winding number and so on and so forth. I'll give you an example of that. So see, you take this rubber sheet, right? You fold this edge. You have this edge. You wrap it up. What will it become? It will become this.
Cylinder.
Yes. So this cylinder is still the same as this, isn't it? Right. Now comes the funny thing. So you say that these two are equivalent, more or less, right? Even though this has been maybe stretched, maybe bent, and so on and so forth. But this is not equivalent to this guy. They have different topologies, right? Or suppose you take this. Imagine a surface which has two donut holes, a two-hole donut. Donut, right? In India, you would call it jalebi. Would you remember that? Right. So there is no way you can take a jalebi, a two-hole donut, and deform it into a sheet of paper, into a continuous flat sheet. It is just not possible, isn't it? So you would say that this topology C, in a very intuitive say, is fundamentally different from the topology of A and the topology of B. But the people use more words, but let us use some very rough words here to get the intuition. Are we together? Right?
Yes,
So,
sir.
right? So that is the meaning of saying that things have different topologies fundamentally. Now, there is something very interesting that you will realize, and it is a joke in the about mathematicians, that if you give a mathematician a donut and a cup of coffee, he will sip the donut and eat the coffee mug. Right? So what does that mean? So you have a coffee mug here.
So that means 3D and 4D.
What's that?
It means like a 3-dimensional and 4-dimensional manifold, embedded in 4-dimensional manifold.
Right. See, think about this. I'm just approximating coffee mug, right? And think of a donut. This is your donut. This is the hole. I'll just mark the hole with a solid. Right? This is the hole. And what you can do is imagine that you took a little bit of the mass here, solid mass here, is a solid 3D donut, and you start bending it a little bit. And then it became like this, right? Then you stretched a little bit, took more material from here, and you stretched it a little bit to this. And then a little bit, you keep on deforming it, and then you take some of the material here and you make it. So now what does it look like?
Same.
It begins to look like a cup. But you can do it, this is again a hole. So you realize that you can do a homeomorphism, a smooth deformation from a donut to a cup. And this is so popular, I just realized that Wikipedia actually put it in its web page defining what homeomorphism is. So I wanted to show you that. I was very impressed today morning, I was looking for it. I suppose the joke has become so popular that, okay, I will now show you the screen here. So guys, look at this visualization. Do you see how a donut becomes a cup? Look at this. Are you seeing the point, guys?
Yes.
So
Yes.
this is the heart of homeomorphism. See, what is interesting is when two things are homeomorphic and when two things are not. When two things are not homeomorphic, it means that they are fundamentally different. So for example, and why do mathematicians play with such silly ideas, you may wonder. They seem to have too much idle time, it seems, on their hand. But it turns out that this is actually much of what we do comes down at heart to these basic ideas. If you want to say, you can go about fields like machine learning, etc., in a cookie cutter way, just this library, that Python library, this R library, and pick up gazillions of things. Or you can sort of go straight to the root, the foundational ideas. I'll give you an example. So imagine that you have a ring that intersects each other. People often give, in the US, it is, and in the Western Hemisphere, it's common for young couples, I don't know if it is still common, to be often given a gift of a ring. But this is supposed to be person A, and this is supposed to be the spouse. And these rings, they're locked in like this. Right? They're locked in. You realize what I'm saying? You can't unentangle the rings. They're looped. Are we getting that? Now, is there any deformation that will open the rings? Think about it. Is there any smooth movement that will unlock the rings from each other, unlink the loops?
No, sir.
Yes.
There is no such deformation, isn't it? And in fact, that is the symbolism of giving young couple, I believe, this sort of ring. They are trying to, I'm not very sure, but somebody here can clarify for me. But I suppose it symbolifies that the two people are joined forever. They should stick together or something like that. Right? That's the symbolism. And newlywed couples are given something. So anyway, so that's that. You can't uncouple it forever. It's forever coupled. So you would say that these two things have completely different topology, isn't it? You can't go from here to this. sort of actually one of the things that I worked on during research in theoretical physics is my research group, it wasn't my idea, it was my professor's idea. They had hypothesized that the reason the proton is so stable and it doesn't decay at all is because it is actually something like this, a knot. I mean, it's sort of in a very rough sense, it is a topological soliton, basically. But think in a very rough way, you can think of it as a knot that you cannot unknot. Right? You cannot go from here to here. So for a proton to decay, in other words, become a lesser thing, or disintegrate, it needs to be unknotted, and it takes tremendous energy to do that. You can't just do it, right? Which is why protons are so stable. I think we know that protons live at least 10 to the 38 years, to the best of our knowledge, is greater than, its lifetime of a proton is greater than 10 to the 38 years. Nothing has that lifetime, right? So it's very, very stable. So that goes again back to the idea that these certain geometries are very stable, and you can't go from that to this would be considered a trivial geometry, relatively speaking, trivial geom, simple geom, compared to this one. Right? So you can't go back to this. Anyway, those are the ideas. Another example is, suppose you take a paper. So you have a sheet of paper, and you align these two rows. You will get a cylinder. You will get a ring, actually a ring. Let me just take a very long bit of paper. So to illustrate the point, just imagine a long strip of paper. And if you align this ring with this, what will you get? You'll get this nice structure. Isn't it, guys? If you tape this edge to this edge, let me call this A, B, C, D. So if A and C are taped and B and D are together, they're joined, what will you get? You'll get this structure. But now let's do something slightly different and do the opposite. We align, and this surface, if you look at it, it will have an outside and an inside, has a and an inside. Isn't it? This is basically your can of soda or your can of food. There is an inside surface and there's an outside surface. But now do a slightly different experiment. Suppose you do the opposite. You connect A to B and B to C. In other words, before you connect these two, you give it a twist in the page. Maybe I can do this and show it to you guys. And you will know that then the concept of geometry, this topology is different thing, will become clear. So see guys, I have this sheet of paper. Can you see it? If I do,
No.
what do I get? I get a
Mobius strip.
Mobius strip.
One
Right now it is a cylinder. Yeah.
It's a cylinder, and this is the outer surface. So it has an inside and outside. But if I give it one twist, then it becomes a Mobius strip. And a Mobius strip only has, surprisingly, one surface. It doesn't have an inside and outside. It has only one surface. Right? So if you start roaming around the Mobius strip, you will realize that you'll come back to the original place after having traversed all the surface. Right? So now, if I tape this thing, is there any way you could deform this just by, without cutting this paper? Is there anything you could do to make it into, you can try all sorts of things, but will it become the simple cylinder again?
No.
No.
Cannot, right? So you would say that a Mobius strip cannot become a cylinder through any homeomorphism. There is no homeomorphism that will take you there. Simple, guys? Right? Yeah. So that is the idea, the core idea we'll talk about here. So now that we understand these words, homeomorphisms and diffeomorphism, diffeomorphism is just smoother ones. And remember that inherent in this is the invertibility of it. You could always go back. That is why I gave the sliding scale, 1 minus t times the original thing plus t times the final thing. So it's a little bit of the original, little bit of the final. At t is equal to 0, it's only the original. At t is equal to 1, it is only the final diagram that you're making. Now, how is that relevant to us? But before we go there, let us start putting tick marks to it. So now what is a manifold? So, so far we understand. Now what is with all this background, what is a manifold? So think of a manifold as a sheet of elastic sheet, right? Which need not be plain, which can be crumpled up. So for example, a donut is a manifold. Donut is a manifold, right? A sphere is a manifold. Any surface that you can think of, right? Smooth, I mean, so long as it is smooth. So the one condition we expect is smooth. You can't just iron a sheet with a very sharp edge and call it a manifold. When a sheet has sharp edges, it is called an orbifold, and we won't deal with orbifold. Machine learning, the gist of it is manifold, smooth surfaces, right? And the surfaces can be in higher dimensions also. So in 3D, we think of 2-dimensional surfaces, right? We live in 3-dimensional ambient space. So I'll use the word ambient. Ambient space is the space in which data lives. So our eyes see data in 3-dimensional space. In this 3-dimensional space, surfaces, when the natural thing we think of surfaces, the surface of a teapot, the surface of a, just a bed sheet on the bed, right? Or my writing tablet or anything like that. These are all surfaces and they all come as 2-dimensional surfaces. But when mathematicians think of surfaces and spaces in machine learning, the first generalization is data comes in arbitrary many dimensions. So let us say that the data comes in p-dimensional space, initial space of p-dimensions. So you generalize from 3 dimensions. See, a human mind cannot visualize higher dimension, but logically we can sort of imagine that data is existing in p-dimensional space. So any surface there would be of one less dimension. Just as in 3 dimension, a surface is 2-dimensional. So in a p-dimensional space, a surface would be p-1 dimensional. Are we together? Any hypersurface. And you would call that a hypersurface. So that brings us to the concept of a hypersurface.
And Asif, one quick question on, so you made a statement about generally in machine learning, we deal with smooth surfaces.
Yes.
Now, would there be a rider that you'll add on to that to say the smooth surface requirement is within an interval?
Bounding. So that is there. So what you say is, see, machine learning, generally in real life when you solve a problem, the input space is not unbounded usually. It can be, but usually is not unbounded. There is some region into which you are trying to model. Occasionally it is possible to model for the infinite extent also. It depends on a situation by situation. So one example that I would give is, let's say you have a sine wave. Now a sine x goes from, for x goes from minus infinity to plus infinity, you can define sine x. So if you're trying to model sine x on the entire interval, the function that will approximate that will be entirely different from a function that just looks at one period, right? Look at this one interval, one period, right? So let me call this a limited box B, and this is the whole thing. So in other words, when you do x going from 0 to 2 pi, the model that you would build, that you will need to build, let me call it gx, would be different from the model that is here. So for example, if you did the ML 100, 200, do you guys remember what did we approximate this with? How many bends does it have? 2 bends. And so we can approximate it as a polynomial of degree
3.
3, right? So we could do it as, like we could do it as a 3rd degree polynomial means. And now instead of betas, I'll use W's, weights in deep learning. W1 x plus W2 x squared plus W3 x cubed. So this will suffice to describe it in B, but it will not suffice to describe it in this interval, right? Because in this interval, there are infinitely many bends. And of course, you would realize that if I want to do this fx, I will have to write a polynomial in infinite number of terms. In fact, that's what it is. When you expand, a Taylor expansion of sin x has infinitely many terms. And many of you would remember that x minus x cube over 3 factorial plus x5 over 5 factorial. And it goes on and on and on, right? Minus x7 over 7 factorial. There's no end to it, right? So the question in machine learning always is, you're building a model for some practical purpose. So what is the domain of relevance of your model? Is it the entire extent or is it a limited extent? All right, Ranjan.
Yeah.
Now, so with all that being said, invariant to all that, you can imagine a surface which is infinite extent. For example, you can think of a plane that has infinite extent, right? It's just an infinite bedsheet in that sense. So a hypersurface may or may not be limited or bounded. All right? So given a hypersurface, if I add one more condition to it, which is interesting, roughly speaking, and this is a very rough way of putting it, roughly, if your hypersurface does not have sharp creases. Did I spell creases correctly, or is it C-R-E-E-S-E-S? I don't remember. Creases.
That's
right?
correct.
Then it is a manifold. What does that mean? So one example of that is, let's say that you take a sphere. Let's take a sphere. So you can take any region of the sphere, tiny region, and imagine there is an ant here. Oh, by the way, do you guys know that in Fremont, at least, there is a massive ant problem that has suddenly come up. Terminix informed me that they're getting 1,400 calls a day about ants. So unexpected result of climate change, because the earth has become so hot and dry that these poor ants are moving into people's home in search of better ambient conditions and some moisture. And they have become, in a very real sense, climate change refugees. So anyway, so imagine that you're, well, that's a digression. I don't know, is anybody else noticing that?
Yeah, in San Ramon also same thing.
Same thing, yeah. So imagine that you're a little ant. If you're a little ant, to you, this sphere, the little bit of surface that you see, and imagine that this is a giant sphere, what will it look to you like? It will look to you simple flat surface, right? Like a Cartesian surface, X, Y. You can draw your XY coordinates. Does that make sense, guys? Right? So this is the ant sitting here. And to it, the world looks flat. So you would say that to the ant, her world is equivalent to an R square, Cartesian flat surface. Would you agree? I.e. a little flat plane.
Yes.
Would you agree?
Yes.
So this little world, the little world that an ant sees, the little world that an ant sees is called a map. Map. Because it's the map that this ant has of her world. Now, what about the next ant? There is another ant here with its own little map. There's other ant, but then suppose you have another little ant who has a world like this, right? The yellow ant. Now, look at the yellow ant. It has its own little map, right? Which is R squared. But there is a problem to it. You know that the sphere is curved. So now, see, in reality, whether the ants can see it or not, there is a little deformation of their worlds, right? Actually, let me make it in white and yellow. Let's say that the world of yellow ant is this. And the world of the white ant is something like this. So now there is a problem. This ant, the white ant has a coordinates, X and Y. And the yellow ant has its own coordinates for the same point P. Yellow ant would say as X prime, Y prime, isn't it? So far so good, guys. And you realize that the yellow ant is sitting here and the white ant is sitting here. And see, the yellow ant and the white ant are not different, because these two maps, one can be diffeomorphed to the other, right? Morph to the other. Means you can continuously change this world to this world. How? Make the ant go this path. If white ant goes to the yellow ant to have a conversation, what will happen? Then the world of white ant will become the same as the world of the yellow ant. Would you agree, guys? So if white ant goes and meets the yellow ant, so it is at the location of the yellow ant. What has happened to the white ant's map? It is identical to the yellow ant's map. Would you agree? Right?
Yes.
So it's like this, you know, the white ant is sitting with its map and it is going and meeting the yellow ant, right? So the thing is, gradually this map will change into this map as the white ant goes, and then white ant comes back, it will get back its own world. Right? Now there is something very interesting. This point P, which is XY, has a different interpretation in this other guy, in the yellow ant's world, which is X prime, Y prime. So you would agree that once again, there's a homeomorphism between these 2 points. There is some function, some way to tell that X prime, Y prime is some function of XY, right? It is some function of XY. You can do that. And so so long as this condition is fulfilled, you say that this surface in which you can smoothly move back and forth, right, is you have a manifold. Roughly speaking, it's a compact, well, there's something Hausdorff compactness, many things here. Technical definitions are there, but I'll keep it to basics. It just means that they're smooth. You can go smoothly from one guy's perspective to another guy's perspective. And this is very real, guys. You know, we all were little ants thinking that the world is flat, right? And now we don't think so. We know that we are on a sphere. So you would say that sphere is a manifold. Manifold, right? Because local patches look like Cartesian spaces, Euclidean spaces. So in other words, criteria is local patches look like Cartesian spaces, right? R, whatever. Here it was R. So I'll just say Rn, some way. So with that understanding of manifold, now we understand all the concepts. And now we are ready to read this paper. Do we understand what is a manifold, guys? This one? Guys, if you don't understand, stop me and I'll repeat it.
Asif, if you can repeat it again.
Okay, so I'm saying that a manifold is something whose local patches, so on which if you put tiny ants on, to each of the ant, her world will look like, for example, on the sphere, let us say a sphere, R2, local regions look flat. i.e. they look like Cartesian space. So this is true for a sphere, isn't it? To the ant, if you want to say, to the ant, look flat. So any kind of a hypersurface, broadly, where this is true, right? And there is a way, it may be curved, curvature is perfectly fine, but if two ants are separated from each other, but they have a way to reconcile their perspectives. So the same point P, I represent as xy, you represent as x prime, y prime, and we have a rule to translate back and forth. Then we are in good shape. Right? We are looking at what we are looking at is a manifold. Am I making sense now, guys? That is all a manifold is. Locally, it should look flat. So for example, you crumple up your bed sheet, and to an ant, the little bit of space that the ant can see looks flat, isn't it? But to us human beings, for the longest time, the earth looked flat because we didn't travel far. So we imagine that if you went too far, you'll fall off the edge. Does that clarify, Anil?
Yes.
Okay. Anybody else, guys? Okay. So, you know, these are preparations to this beautiful blog at this moment. So this is a manifold. What is the topology of the manifold? Is the structure. Think of it roughly as the structure, right? Whether it looks like a flat, whether it has a hole in it or whatever it is, that is it. Homeomorphism and diffeomorphisms are smooth transitions from one looking one way to another while still preserving the topology, right? You don't change the topology of the manifold, you just bend it a little bit, right? Or stretch it out and bend it and so forth. So, for example, a cup and a donut, they are homeomorphic to each other because you can smoothly transition a donut into a cup and vice versa.
Sir, one question.
Yes.
So the manifold locally it will look flat, but non-locally, like how it will be, it could be flat, globally also, right? Flat or a deformed
Yeah.
surface.
A hypersurface, a hyperplane is globally flat, right?
Right.
So, but it need not be. It could have bends.
It could be deformed surface in any shape, any hyperplane, basically. Hypersurface, I mean.
That is right. In fact, just as a small digression, uh, what Einstein said in his general theory of relativity, once you understand manifolds, what he said was something very simple. He said that if you think of space-time itself as a fabric, as a manifold, think of it as a fabric of space-time. It's a four-dimensional manifold. But then what happens is that just as you take a surface and you put a heavy object on a rubber sheet, what will happen? It will develop a bump, isn't it? If you take let's say, and this is again a digression from this blog, but I thought I'll mention it to you. You take a plane, this is two-dimensional, but imagine it's four-dimensional. If you put a heavy object here, you expect that a deformation will form on the fabric, on the elastic fabric.
Right.
This is it. And so now imagine, so with this deformation there, and I'll just exaggerate the deformation here, right? Here. What will happen to a point that happens to be traveling in a straight line? It will come and it will get bent because the surface here is bent. Do you see that? A particle or a body that is traveling in this direction will get bent, isn't it? It's spinning by, but then you see there's this deformation and it bends. You can see, you know, in the mall you go, there this little, this surface is kept there for children and they'll roll a coin and the coin will spin many, many, many times and then fall at the bottom. Do you guys remember that? Seeing this in malls? So this is it. So imagine that unknown to you, the space-time itself has developed a curvature because here is a big object, heavy object, let's say the sun. And this happens to be an asteroid or something like that. Right? And so what happens is when the asteroid comes within the solar system or sort of comes within the orbit, it gets bent automatically. And gravitation, the explanation of gravity is that the reason gravity exists is because a mass is, I mean, the explanation is whenever you have a mass in space-time, it deforms the space-time manifold. And the degree of deformation, the curvature here is directly proportional, the degree of curvature is directly proportional to the amount of mass that you have here, or the energy that you have here. In fact, roughly speaking, people talk about G mu. I won't go into the details of it. That is all that general theory of relativity says, that the curvature is energy, and the amount of energy at a place is directly the mass, controlled by the mass there in the space-time. And that's why one thing gets pulled into the orbit of another thing, or gets attracted to another thing, and so on and so forth. So this is it, guys. You know, when you understand these concepts of manifolds and homeomorphism, etc., a lot of these deep ideas, they begin to become quite simple after that. So now, but let us go back and make progress on our blog. Huh? So we understand homeomorphisms, we understand manifolds and topology. Now, the fundamental hypothesis. What is the manifold hypothesis?
So, just a second. What's the
Hold on.
difference between homomorphism and diffeomorphism?
So let me write this sentence down. What is the manifold? And this is fundamental. Is someone asking a question?
What's the difference between homomorphism and diffeomorphism?
I can't hear you, Harini. I think you are speaking, but I can't hear you clearly.
Okay, what is the difference between homomorphism and diffeomorphism?
Anybody can repeat that, what she asked?
Asif, your third question in your bullet point, if you go to the top.
Homeomorphism and diffeomorphism.
Yeah, the difference between those two, yeah.
Just think of it as very smooth transitions are diffeomorphisms. That's all. When you gradually transition one thing into the other, if you do it very smoothly using the mapping, if the mapping function is differentiable, it's a diffeomorphism, right? So in other words, if x goes to y, and there is a function fx. If you can take the derivative of f, if it exists, it's a diffeomorphism. Right? And what it means is, geometrically, what does it mean for a function to have a derivative everywhere? It is just a fancy way of saying that the function is smooth. Are we together? That's all it means. Not all functions can be smooth. It can be continuous, but it need not be smooth. For example, this function, is it smooth? No. There is a non-differentiable point at the bottom. Which is why I said, this is a crease, this is a wrinkle, right? This is a very strong crease here. So long as you don't have creases, so long as you don't have these edges in your function is a diffeomorphism. Simple enough, guys? Okay.
Yes, sir.
Yeah. So now we will go to this manifold hypothesis. So the best way to do that is, I'll go back to the foundations that you learned. See, regression. The classic regression is there is an x point and there is a y, which is a target variable. Right? You do things like this. You have points like this. When you have a point like this, you become hopeful and you say that a good prediction line is this. Y is equal to 1x. This is how you learn in elementary machine learning books, isn't it? Up to error term. Am I making sense, guys? Does this look extremely familiar now?
Yes.
So this is, but what is a line? Now just ponder over it and think back. We went from, we are saying that data is in R squared, right? Data is in R squared, but so ambient space, this is the ambient space. where data is presented to us, right? In common sense terms, what it means is we will be given a table, X, Y, a table of data, right? So we are given a two-dimensional data. But the only hope you have of solving this, right, is that you find a one-dimensional line. Yellow is a one-dimensional line. Right? This is R1, i.e. R. It's a one-dimensional line. Now, look at an alternative data set. If the data set is like this, so let me call this data set A, data set A, data set B. Now, in which of these two cases will a regression model be successful?
A.
And why is that?
There is pattern mapped by line.
See, there is a relationship. Y does have a relationship to X, and it shows itself by the fact, a linear relationship, that all the data points sort of reflect that relationship. Here, all you can say is that, if anything, you can say Y and X are completely unrelated, seem to have no relationship, isn't it? Would you agree, guys? So you wouldn't try to build a model here. In fact, your model will be a null hypothesis. There is no relationship between the two. Now observe the situation where there is a well visible relationship in A and a lack of a relationship in B. What can you tell about the data points in A versus data points in B? Geometrically, what do you observe? Anybody would like to venture a guess? Geometrically, what's the distinction between A and B?
So is A is like a stretched surface?
Sorry, A is like a?
Like a stretched surface?
No, I'm saying data,
Oh.
two-dimensional data, XY data.
Oh, okay.
Cases. In one, the data looks like that. In the other, look at the white points, and the data looks in the second case, B, like what it is in the lower graph. So geometrically, what are some of the differences that you see when you just visualize the data?
So space B is more dispersed. And space A is more concentrated.
The distribution of the data is different.
Line and a space, a line and a surface.
Yeah. So, you guys are coming to it. See, if you look at B, the data seems to occupy all of the two-dimensional surface, the two-dimensional space, input space, right? It's scattered everywhere. But what do you see about A? Most of the data is close to a lower dimensional surface, namely a line. Do you see that almost all the data points are either sitting on the line or close to it? Isn't it, guys? Right? We can say that all the points are proximal to the line, isn't it? So now let's try to generalize from that. What about this? I could have the points here. It need not be a line. Suppose I have a situation like this, X, Y. You would still say that there is a relationship between X and Y, and you can do a regression model here. You have a one-dimensional curve, one-dim curve, right? That the data is proximal to, that the data is proximal to. So generalization of this is that If you have a relationship in a plane, you can build a successful regression model, which is a relationship between y and x, if and only if the data are close to some function, some curve, right? And what I'm saying is very common sense. I'm saying that that if you're looking for y is equal to fx epsilon, this f is nothing but a curve 2D. Do you agree with that, guys? This function is a curve, and so most of the data has to be close to the curve, right? Up to this error term.
Okay.
Feedback that this looks obvious. Does this look obvious, guys? Simple, right? Some function. Now, what you say, now observe something. In higher dimension, so suppose it was 3D, your y would be some function of x1, x2, and this would look like a surface. All the data will be proximal to this surface in 3D, and in higher dimension, so now generalize it to higher dimension, and y would be some function of, so let us say that dimensionality of this is Rn. So the vector space, let me make it 1 plus 1 because it is x, the dimensionality of x and y. You would say that y would be some function of x, isn't it? And this would be n-dimensional hypersurface. Does this make sense, guys? Is this generalization making sense? In 2 dimension, the function is, its function lives in 1 dimension, namely is a curve. In 3 dimensions, the function lives in 2 dimensions. In other words, it's some surface. And you can generalize to higher dimension. As simple as that. So when you say that this is true, you're making the hypothesis that all machine learning is possible. See, you can find a relationship only when a relationship exists. And the existence of a relationship means there is a hypersurface in the ambient space, right, which is of a lower dimension, and the data is close to that. Most of the data is sitting on it or is very, very close to it, up to an error term, right? Otherwise, you wouldn't be able to do machine learning. Geometrically, it's a very obvious statement, isn't it? So now we understand this manifold hypothesis. Manifold hypothesis just says that just says the data given in ambient space of d dimension, let's say of capital D dimension, will actually live closer, proximal to a lower dimensional embedded manifold. Embedded means this line, this curve is sitting inside that higher dimensional space. Embedded, lower dimensional embedded manifold. Manifold is just your hypersurface. So this is the, otherwise, you cannot build a model. Otherwise, you can't build a model. So this is the manifold hypothesis. So far, so good, guys. And
so I say, what is that like a space RD will actually live after that? What is the word?
Will actually live proximal to a lower dimension.
Proximal, okay.
Means close to proximal, close. Just use the word close with that said. Close to a lower dimensional embedded manifold. Otherwise, you cannot build a model. So guys, do we understand it? I hope this was something by now fairly self-evident. Would you say, Pradeep, are you getting it?
Yes, sir.
Okay.
It's good.
Yeah. All right, all of you are good with that, right? Okay, so then we are ready to read this beautiful block. Let's go from the beginning and try to read this. So what it says is that imagine that all the data point that you have, by the way, this picture in this in the printing, because I made an image out of it to put it into this notepad. So it is actually like this. It is one big blue line, like this, and a red line, like this. If you read the original blog, it's like this. So data is here or here. So suppose you're trying to write a classifier. You know that you need a decision boundary, and how should your decision boundary go? It has to go like this in this space, isn't it? So if this is your x1 and this is your x2, and these are your data points, it turns out the data is most of the data points are here. He has made a solid line. Realistically, you can make it a little bit more rough line in the sense that data will be proximal to this surface. Suppose this is the reality. You want to write a classifier, you need to build a decision boundary that looks like the dotted green line. That makes sense, isn't it? Speak up, guys, please.
Right.
Yeah.
Yes.
That makes sense, right? Okay. So now how does it do that? What it will do is when you take a neural network, so when you say that I have a neural net, ultimately, right? So suppose this is the input, x1, x2 are the input that go in, and then there's some hidden layer, right? So there's hidden, and there's hidden, and so forth. At the end of it, what comes out is some transformed variable. Let me call it xa prime, xb prime, that are coming out of these nodes. These are the responses of this node. And then it finally goes at a last node, right? The logistic unit at the end. So you know that the last thing, what does it draw? What does a logistic unit draw? If you recall, a logistic unit, logistic regressor builds a what? Builds a linear decision boundary. So what does it mean? If this guy has to successfully be able to classify, what you need to do is you need to take this space and somehow do a homeomorphism of this, to some place where a straight line, a straight decision boundary, let me mark it in green, a straight decision boundary would suffice. So this is the decision boundary that this line is, the last unit is building. So what, for that to happen, somehow the data has to become, the blue has to somehow be here, and the red curve somehow has to come here, completely in this region and this region, isn't it? You need to take the original manifold and you need to deform it into another manifold in which a straight line goes through, because that's what the last unit is doing. But then for a straight line to be the correct classifier, all the blue points should be here and all the red points should be here. Make sense? Right? So that is what it does. And you see that happen. You look at this. So you may have all sorts of hidden layers, not just in the hidden layer, not just two elements, you can put more. But at the end of it, for you to draw this decision boundary that is here, we need some representation that divides the data. And you notice this is a green line. Where is a green line? This is a green line, right? So all the blue points are up and all the red points are below, right? And so what has happened? Do you notice that this curve has been deformed? This curve, let me use some other marker. This, look at the blue curve. Blue curve has become this curve. There's a homeomorphism of this curve into this curve, and there is a homeomorphism of the red curve into this. isn't it? Gradually, it has been deformed from one to the other, isn't it? And so this is your, like I said, that the new axes are XA, XB. This is your XA axis. This is your XB axis, right? And the initial axis, if you think of them as X, what is it? X1? What did I initially say? X1, X2, right? This is your X1 and this is your X2 axis, right? So initially, this manifold that you have here, it is gradually deformed to this other manifold where the curves drawn on the manifold, their shape has changed, isn't it? But when the shape changes, the beautiful thing that happens is a straight line can cut and separate the two curves easily. The green line now, straight green line, which is the logistic layer, the last logistic layer, decision boundary, of the last output layer. Isn't it right? Does that make sense?
Yes.
This is it. And this is the beautiful idea that he's trying to say. And then he gives this visualization. If you see how it does it, how these functions do it, it is provable. And the thing is, the proof of this is quite simple. If you think about a point, let us look at the proof of it. Suppose you have a point X and you translate it to X plus omega naught. Do you think that this is a homeomorphism? All you have done is you have taken a point and you have moved it with omega naught, right? This becomes X plus omega naught. Is this a homeomorphism? If you take a plane and every point you shift, will it still smoothly transition to the other plane?
Yes.
Yes.
Should.
A translation, therefore, is a homeomorphism. This is easy. Translation is homeo. And is it invertible? How do you invert back to the original point? You just subtract W naught, right? Likewise, the next factor, suppose I take X and I multiply it by W1X. Is this a homeomorphism? It is a stretching, right? You're just stretching it by an amount W1. Make sense?
Correct.
Right? So is this invertible? Of course, you can go and divide it by W1 and you'll get back the original point. Right? If I divide it by W1, you'll get back the original point. So this too, scaling, is basically stretching. 2 is a homeomorphism, is invertible. So now look at this. Suppose you have a function z is equal to W naught plus W1 x1. And now let's go to 2 dimensions, x1 plus W2 x2. You would agree that this is a homeomorphic transform. This is a smooth transition.
Yes.
All you have done is stretch the plane a little bit and moved it around a bit, right? And now comes the interesting thing. After that, suppose you apply a tan h function, a sigmoid function of some sort, right? Suppose you apply a tan h z. What is tan h z? E to the z plus e to the minus z, e to the z minus e to the minus z. I hope I got it right. Correct me if I got my pluses and minuses in a twist. But this is it. This is your tan h. Now, this function, is it, what about this? Does it take z to a homeomorphism of z? When I go from this, tan x z, is it a homeo? And the answer to that is yes, because this function is differentiable. let me write it, because.
So as if I think you changed the sign for tan h. It's the e to the power z minus e to the power minus z.
Oh,
and
right.
then positive on the bottom.
Positive. Okay, there we go. Because I can differentiate tan H Z is differentiable with respect to Z. So in other words, it's a smooth function of Z. So I can gradually deform Z into tan H Z, right? Therefore, it also is a diffeomorphism. And so what it means is that in my layers, when I take this network, let's say any one of these nodes into which X1, X2 goes, what is it doing? It is doing a tan H of Z, where Z is this transform. So you're doing a set of homeomorphic transformations, and the accumulated thing is still a homeomorphic. So your points X1, X2, ultimately, they just smoothly moving to some other point in space, which is what we see. If we go here, every point here is smoothly moving to some point here, right? Do you see this nice square grid? And what has happened? The square grid has been deformed. Do you see that the same grid is now stretched out? You can see a bulge here, you can see a squeezing here, but it is a smooth transition from one to the other. And that is what neural nets do. What they do is they deform the space continuously, the input manifold continuously, till the two classes become linearly separable. And when they are linearly separable, the last output layer just draws a straight decision boundary for a classifier. Right? So that is what he's trying to say. And much of the paper actually talks about that. Then he goes on and says, you can do more than that. If you think about this one, this picture. So far we understood here, so far guys, right? Did we understand?
Ask a question.
Yeah.
So when we say the transformation, so is it like a linear transformation or is it a affine transformation?
No, it is, see, it is a smooth homeomorphism. It's a non-linear.
Okay, it is a smooth, okay. Yeah.
Right? So it's a deformation. See, imagine that you have an elastic sheet, right? And then you put your fist into it. You realize that it's a non-linear deformation, but it is still a smooth, gradual deformation, isn't it? But it's non-linear inherently. The moment you bring in tan H is non-linear. Up to Z, it's a affine transformation. Z as W0 plus W1, X1, etc.
Oh, okay, got it, yeah.
Tan H inherently introduces a non-linearity. Then comes a beautiful thought. So you can sometimes look at the data and tell, remember this was a point I was telling you about, you can look at the data and tell how many nodes you need in your neural network. So suppose you solve this problem. You have the red in the center and blue outside, right? So if you take a neural network with two nodes, let me take that in some color. Suppose you build a neural network with only two nodes, X1, X2, and what do they produce? These are the two hidden layers, right? What do they produce? They have the different weights. So how many weights will be there? There'll be 4 weights here and a bias term and a bias term here, right? So they will produce, let's say XA, XB. And let's say that XA and XB go in and feed into the output layer, right? So now think about it. XA, XB, whatever it is, it's a homeomorphism, smooth deformation of this. Let me call it X1, X2. It would be a smooth deformation of this to this, isn't it? Now you can convince yourself that there is no, whatever stretching you do, the red circle will stay inside the blue circle. If you stretch it a little bit, you might get a red circle here and you might end up with a blue circle here, isn't it? But you won't be able to take the red out of the blue, right? So there is no straight line that you can draw. There is no straight line that you can draw that will separate the red from the blue. Actually, I should have used.
We can pull it after.
Sorry. Let me make the blue into a blue properly first. Blue. Right. So there is nothing that you can do will convert And you can in your mind try to stretch and do whatever you want to do with this plane. There is no way you can go from this two-dimensional surface to this two-dimensional surface. Now, give it a moment in your mind and see whether what I'm saying makes sense or not.
What happens when we pull it up?
Harini, you need to fix your microphone. I can't hear you at all.
What happens when we pull the red up?
Try dialing. Harini, please do one thing. Take your cell phone. You can use your cell phone to dial into this Zoom. Try that because your laptop is not working out.
I think she's asking what if we pull the red part up?
Up, exactly. But that is, you're now going to 3 dimensions.
All right.
Harini, you have just the right idea. Your idea is correct. You're now lifting the thing up. So to lift it, you need one more dimension, isn't it? Right?
Yes.
What does that mean? You mean that this thing here, you need one more dimension basically. You need to go to a 3-dimensional space. You need one more node coming here, which will produce XC, a 3rd-dimensional space. Because if you could lift it into, if you could give me a 3-dimensional space, all I need to do is make the red in the 3rd dimension, make the red sort of stand out here. And in this plane, again, the same thing about this plane, and the blue part to be a circle here. And therefore, I can easily make a decision boundary like this. That's the point you're making, Harini, isn't it?
Yes, sir.
Okay. Excellent point. That's exactly the right point. And there we go. So in other words, what have you proved? You need at least 3 hidden nodes in the hidden layer to be able to solve the problem. And that is the point he's making, that see, sometimes by just looking at the topology of a problem, you can tell what neural network you need. And that was essentially the point I was making in the class also. Remember, I took a slightly different example. I took the example that if your data set is like this, what was it? This is all blueberry kind of thing, and this is some red colored berry. Oh, what happened here? This is all red berry. You need at least 1 hidden layer with how many nodes in it for this problem?
2.
2. You need 2 nodes in this. And let's reason why. So I gave the explanation that you need 2 hyperplanes to solve this. 2 lines to solve this. 1 line per logistic unit. So you need 2 of those magic boxes to solve it. Now let's reason the way Olah reasoned it. He's saying that, see, suppose you look at it as a manifold. Can I somehow stretch it in such a way that this begins to look like a solvable thing? Yeah, I can, right? If I stretch it really, really hard, what I can do is gradually, I can make it with, if I stretch it really hard, I can make all the blue points sit up and all the red points sit here effectively, and then I can draw a thing like this. So for something like this, though this would be quite a stretch, maybe a better stretch. You guys can think of a better deformation. Maybe this is not the right one. By the way, we can find that out. Why don't we do it as a lab homework? Let us see that if you put 2 layers here, you give it x1, x2. I'll take this data, and let's see what xa, xb turns out to be. And let's plot xa as b. We will also learn whether it looks like this or looks like something else. So let's take this as a homework and say, what does xa, I'll write it here. What does xa, xb space look like? Play around with it. It's very simple. You take a data, something like this, and you just feed it to 2 layer, a hidden layer with 2 nodes, and then you get your answer. So that is the gist of what he's saying, guys. Then he goes on to other things. So he says that the moment you take a 3rd layer, the red lifts up here. separates out. And you see it happening here. You see that the red has lifted itself out from the blue plane. Right? The blue is here and the red is here. It has deformed. Obviously, it doesn't look like a circle here. I oversimplified it. It gets stretched out. But in a three-dimensional surface, now you can do a separation. Right? You can simplify this even more. Suppose your data is like this. Is there a green line that I can draw that will separate the blue from the red? I cannot do that. Isn't it, guys? Look at this data. But if I lift it, if I could somehow do this, and then this is blue. Let's say that the blue is here. Where's the blue part? This is blue. This. Now I can draw a decision boundary that goes like this. And that is that. That's the basic idea, right? It becomes even simpler that you need one more dimension to do this. So in other words, to solve this problem, you need, again, how many nodes do you need? You need 2 nodes to do this, because you need to produce XA, XA, XB. You need a 2-dimensional plane to solve this. So that's how you reason about solving problems, looking at the data and solving problems. Now he goes on to something else. He says that, see, there is a problem of knots. Suppose you're given data like this. People in knot theory talk of knots and unknots. So when you tie your shoelace, it is not a knot. We think we are tying a knot, but mathematicians would disagree and they would say, actually you're tying an unknot, because it can be, it is an unknot because you can actually unravel it. You can pull the strings and then it will open itself out. And when you pull the string gradually, so what you have done is that what you think of as a knot has gradually deformed into the straight string. Do you see that, guys? And therefore, it's not a real knot. Whereas what is a real knot? A real knot is what you see in the picture above. This is a real knot. Why? Because now you have these 2 rings. This is the ring that I was talking about that's popular in the US, I suppose. The young couples are given this kind of a ring. This thing, is there any deformation that will classify this data? Think about it. Is there anything you can do to these rings such that the red separates from the blue?
You can go to the 4th dimension and then separate it.
You can go to the, yeah. So what you can do is you can keep going to higher and higher dimensions until you can separate it. But suppose I say, no, you have to stay in 3 dimensions, then what do you do? Then you can't separate it.
Yeah, 3-dimension you can't separate.
And so what happens is that, see, it is a fact that all knots are unknotted in higher dimensions. Sort of a general statement. I think that statement is true. Maybe there are some peculiar knots that cannot be, but it can be, right? All knots can be opened up in higher dimension. So that's that. So where does this all lead us to? It's just a way of thinking about what neural networks do. So, you know, this week we gave to the fundamentals of neural network, understanding what do they do, and having a strong geometric intuition, at least I find, helps a lot. Right? That's that. Then the rest of it I won't go into. Then there's some speculations and so forth. But this was the idea that I wanted us to cover in this blog. And that is it, guys. So I hope it gives you some intuition of what exactly those networks are doing with our data. And why do they work?
Yes, if this was a good paper, and the fact that you picked it out for us to read kind of gives an opportunity to read a very focused piece to understand something fundamental. Thank you.
You can also show, sir, Klein bottle example is good example.
A Klein bottle is a great example. Theoretical physicists love it. Great that you brought it up. You know something very interesting about Klein bottle? You think that Klein bottles can only exist in 4 dimensions. And yet, people doing image processing showed that local patches of images can be mapped, like there's a homeomorphism of a patch of an image because of the color gradients, the gradients and so forth, to, of all things, a Klein bottle. If you guys are interested, we can discuss that paper. Well, actually, take it as a self-reading, because next week I have a different topic we will discuss in a new paper that we will discuss next time.
Okay.
But it's something to know that these beautiful geometric shapes are all around us. It's a reality that we don't see, and it's there. In fact, images and patches of images are mapped to the most natural mapping of patches of a natural image is to a Klein bottle.
So can you hear me?
Now I can hear you clearly.
Okay. I have, like, when you say now we found the linear, we found the decision boundary in a higher dimension space, right? The knot and all. So as we used in kernels, so that result is used in the lower dimension space by the system to solve it, or how does it come? Do we have to come back?
The idea is the same. So in many ways, you can see that it is the same kernel idea. What you do when you apply all this hidden layer with many neurons is you're lifting data to a higher dimensional space where the data becomes separable.
Okay.
Right? So there is a very deep connection between all of this and what we discussed previously. See, all of these fields, right? All of these ideas are very interconnected.
Okay, yes.
Same idea.
And manifold, is it mandatory it need to be a flat surface always, or only the Cartesian space it need to be flat?
No, Harini. The whole point is manifold is a general hypersurface. So a crumpled up bedsheet in your house is not flat.
Yeah.
Right. So here's the thing. You're a mom. You'll know this. Every morning you make it a flat surface.
Correct.
And your child sleeps in the bed, and next morning, what do you find that surface to be?
Crumpled up. Yeah.
Crumpled up. That's your manifold.
Okay. So it can change. Okay.
In shape. The only condition of a manifold is that if you are an ant sitting on that, locally it looks to you flat.
Okay.
Right? And also manifolds not only have curvatures in the ambient space, they also have stretching. Right? So for example, it is almost like, the bed sheet has some amount of spandex or something in it, and your child just finds it and takes a big ball and wraps around it and so on and so forth. So there is a bulge in the bed sheet because there's some amount of elasticity to it or spandex in it.
Okay.
I don't think anybody makes bed sheets with spandex, but just hypothetically.
Yeah. Okay.
So it can have stretch, deformations, anything. The whole point of manifold is it's a generalization. If it is absolutely flat, it's a trivial manifold. That trivial manifold it's a hyperplane. But you want a sphere. The surface of a sphere, for example, is a manifold. It is stretched. Right? But locally, if you sit anywhere as an ant on a sphere, it looks flat, isn't it? In fact, for the longest time, we all lived on this big sphere that we call the Earth. Well, not a sphere, but somewhat like a sphere, like an apple. And we all thought that the Earth was flat because why? We are like ants. We see only a little bit, and wherever we looked, our eyes were telling us that the world is flat. So therefore, the Earth is a manifold. Surface of the Earth is a manifold.
Okay. So just to make it clear, so when we see a small surface like an ant, that needs to be flat, right? For it to be a manifold. And it is always flat in the nature?
Yeah, so the idea is why are we putting the emphasis on the flatness? See, flatness, local flatness, any function that is differentiable such that you can find the derivative of x, locally if you look, it will look flat. Do you see? Locally it looks like a line, right? And so in higher dimension, this curve becomes a surface. So locally it looks flat. So when you say that locally it looks flat, all you're saying is, in many ways, you're saying that it's a smooth differentiable. It's a smooth surface. Right?
Okay.
That's all. And one very rough way of carrying these thoughts around is, think of a manifold as just a smooth surface.
Okay. Thank you, sir.
The opposite of that would be absolutely like, edgy bend like this, right? Or even a bend like this, or discontinuities, right? Gap. That is not a manifold. If you have tears in it or gaps in it, or if you have non-differentiable, non-smooth points in it, then it's not a manifold. All other things, generally speaking, the sort of data space machine learning people look at, they are all manifolds. Right?
Okay, sir.
All right, guys.